Hello everyone, welcome back to Professor Z's Academy. Today we'll be covering electrostatics, electric field, and Gauss's law. Let's begin by discussing what exactly charge is. So charge is a fundamental intrinsic property of the particles that make up matter, right? So as you all know, uh, all matter is made up of atoms, and each atom is made up of protons and electrons. Now there are two types of charges. There's a positive charge and there's a negative charge. Protons have a positive charge, while electrons have a negative charge. Now, because these charges come from electrons and protons, that means every charge is a multiple of a charge of an electron or photon. And what I mean by that is that if we denote the amount of charge that an electron has with negative E, because it's negative, and a proton with E, because it's positive, what that means is that every object that is charged, that charge is equal to a multiple of E. So it'll be 6E, it might be 8E, it might be 100E, but it can never be something like 3.57E because it needs to be made up of a whole number of electrons or protons. Now, in the real world, most objects are neutrally charged, meaning that their total net charge is a zero. It's neither positively charged nor negatively charged. But that doesn't mean that they don't have charge at all. What it means is that they have an equal amount of both positive and negative charges, which balance out and create a neutral object. Now, the reason that you can't have a zero charge is because charge cannot be created or destroyed. It's called the conservation of charge. So even though it has a net zero charge, it's still just the addition of protons and electrons that all cancel out, creating a net zero. Now, there are two types of materials. There's something called a conductor, which allows for the free movement of charged particles within the object, meaning these electrons can go anywhere in the conductor. But then there's also something called insulators, which means that the charged particles within them are fixed and they cannot move. So regardless of what happens to the object, the charge will always stay in this position. Now, with charges, what happens is that like charges repel while opposite charges attract. What does that mean? It means that if I have something that is positively charged and another thing that's positively charged, they're not going to want to be near each other. So they apply a force on each other away from each other. But in the case of something positively charged and something negatively charged, they're actually going to attract to each other, and the force is going to point towards each other. So the next question that comes up is, what exactly is this force? What is the magnitude of the force of attraction? And this question was answered by Coulomb, who stated that the magnitude of the force, the electric force, from one charged particle to another is equal to K, the magnitude of charge 1, which is denoted with a Q, times the magnitude of the second charge, divided by the distance between them squared. So K Q1 Q2 by R squared. You might be asking what K represents. K is a constant called Coulomb's constant, and it's equal to 1 divided by 4 pi times the epsilon naught, which is denoted as the permittivity of free space, the electric permittivity. But in air and in free space, it's roughly equivalent to 9 times 10 to the 9th. Now, in honor of Coulomb, the units for charges are actually coulombs. So notice that these charges, they have a magnitude symbol around them. Because what happens is the magnitude of the force can't be negative. So if we had an electron or a negatively charged particle, we can't put in a negative sign here because then we get a negative magnitude, which doesn't make sense. So we take the magnitude of each charge and multiply them together. And you might be asking what direction the force will be applied to. Well, as I said before, like charges will repel away from each other. So the force on these positive particles would be away from each other and be equal to KQ1 Q2 by R squared. But for like particles, they'll go towards each other. So the force will be pointing towards the negative, towards the positive, and both of the forces will have a magnitude of kq1, q2 by r squared. Now, in case you're also wondering, the vector form of the Coulomb equation is denoted as k q1 q2 by r squared times the unit vector r. Those of you familiar with vectors should be able to understand what this means, but essentially in the direction of r, you multiply that by kq1 q2 by r squared, and that'll be the force vector. So if kq1 q2 by r squared is negative, meaning that both of them have opposite charges, the force is going to be in the opposite direction of the distance away. So we usually take the distance from a particle to another particle, pointing outwards. So it'll be pointing towards the particles if they have opposite charges. But if they have the same charge, the force will be pointing away from the particles. Let's do a quick practice problem. If I have a charge here with a magnitude of 3 coulombs, and another charge here with a magnitude negative 3 coulombs, and they're 1 meter away, what is the force on each particle? Well, if we whip out Coulomb's law, we'll find that the magnitude of the force is going to be 9k over 1 squared. And I'll just keep it in terms of k. So now the question is, what's the direction? Since these are opposite charges, they're going to want to attract to each other. So the 3c wants to go towards negative 3c, and the negative 3c wants to go towards the positive charge. Each of these has a magnitude of 9k, where again k is Coulomb's constant. So actually it'd be something like 81 times 10 to the 9th. Yeah. But the question is, how do these charged particles provide a force to each other if they're from a distance? Right? Usually when we think of forces, we think of something pushing and pulling against each other. So the so-called action at a distance can be modeled through an electric field. An electric field is basically a map of the force vectors from a charge. In other words, it's the direction that a positive charged particle would go in if it was placed there. The formula reflects this because the formula for an electric field, which is a vector, is equal to the force vector for the force on a particle on another particle divided by the charge of that particle. If you don't fully understand, we're going to go through an example right now. Let's take a look at the electric field of a charged particle, let's say positive. So if I were to place another positive charge here, the force would act in this direction, right? If I were to place one here, the force would act in this direction. If I placed another positive charged particle here, the force on it would act in this direction. And if we keep doing that, what we're going to end up with is something called electric field lines. And what it's saying is that if we place a positively charged particle next to this particle right here, it's going to go along the direction of the field lines. That's the direction that the force will take it in. Now, for a negatively charged particle, the field lines are actually going to point into the particle, because for a positively charged particle, it's going to want to be attracted to this negatively charged particle. And now, the thing to note is that these diagrams, they're for a positively charged particle, meaning that if I placed an electron here, or a negatively charged particle, it wouldn't go in the direction of the field lines. Actually, it would go in the opposite direction. It would head in the complete opposite direction, along the field lines. The force would have the same magnitude, but just in the opposite direction of the field lines. And if I placed another negative particle here, it would be repelling away from that negative particle, and the force would be in this direction. Let's now talk about electric flux. So flux, denoted by the symbol phi, can be thought of as kind of the flow of electric fields. And what that means is, if I imagine a river, right? If I take the cross-section area, there's kind of water flowing through this rectangle that I've created. In a similar way, if we take a rectangular surface, an arbitrary rectangular surface, with the normal vector A, and we have electric field lines passing through this rectangle, we can say that the electric flux, which again is the flow, is the magnitude of the perpendicular electric field lines times the area of the rectangle. Now, this is commonly also written as E A cosine theta, because it needs to be the perpendicular, where theta is the angle between the normal vector. So if I draw this out over here, and I have a normal vector, and I have an E field pointing this way, so this E is the normal vector. Theta is going to be the angle between them. So E cosine theta is going to be the direction that's parallel to the normal vector, but perpendicular to this plane. And now those of you familiar with vectors can see that this is going to be the dot product of E and A, where A is going to have the magnitude of the area of the rectangle, but in the direction of the n vector, the normal vector. Now you might be asking, how can we calculate the electric flux for surfaces that aren't rectangles? So let's say a circle or a sphere would be better. What we do is we kind of zoom in onto the surface of a sphere, and we take an extremely small section, which I've drawn right here, and if I expand this out, you'll notice that it's roughly flat, and it has an area of dA, where dA just means a very small amount of area, right? So if we use the same formula, we'll get E dot product times dA. And recall, just keep in mind that this just means it's going to be E times dA cosine theta, where theta is the angle between the normal vector and the electric field vector. And this is just for one small part of the sphere. So what we need to do is we need to add up all these electric fluxes that we've calculated over the entire sphere. This is integration. So electric flux is defined as the integral of an electric field line dot dA, which can also be written as the integral of E cosine theta dA. Now, you might be asking yourself, what is electric flux used for? Well, it's used for an important theorem law called Gauss's law. And what Gauss's law does is it relates the electric flux coming out of a closed surface to the charge contained within a closed surface. And the formula for this is that a closed integral, which has a symbol of an integral symbol with a circle around it, and what that means is that instead of just a rectangle, for example, it needs to be a closed surface, meaning it needs to be a shape that's hollow. So like a sphere, or it could be a cube, just anything that is closed and hollow, right? But the closed integral of E dot dA is equal to the charge enclosed within the surface, meaning inside that hollow surface that we've created, the charge that's inside it, divided by epsilon naught, where again, epsilon is going to be the permittivity, the electric permittivity. And now Gauss's law is important because it allows us to prove important theorems about conductors and also allows us to derive electric field for non-particle charges. So let's go through an example of that right now. Let's look at a conductor. So let's say that this surface is a conductor. And you may have heard that the field inside the conductor is zero. Why is that possible, right? So if we have all these charges on the conductor that are freely able to move, if we had an electric field within the conductor, what would happen is that these charges in response to the electric field would move around. But this system has to be stable. It has to be in a stable way. So that means the charges can't be moving. So that means there's no electric field within a conductor. All the charges are just there with no electric fields within the conductor, because otherwise the charges would move and they wouldn't be it wouldn't be a stable state. Equilibrium state, if you will. Now, we can know this just using intuitive reasoning. But now with Gauss's law, what we can prove is that all the charges on a conductor are only going to be in the surface, meaning that within the middle of a conductor, there's not a single charge. How can this be? Let's take a cross-section of the surface, right? So this is a 2D view. This is supposed to be a sphere, for example. If I take a cross-sectional view of this conductor, and I draw a Gaussian surface in the middle. So let's say actually I make a mini sphere inside the conductor, right? So this is the conductor, and ignore the cross section. We're going to take the whole sphere, and inside this conductor, I make a little imaginary sphere, which we'll use as our Gaussian surface. Now, we know that the electric field inside should be zero. There's no electric field lines coming in, and there's no electric field lines coming out. Okay. So if we take our integral of EdA, what we'll find is that E is zero. So this flux is going to be zero. But since Gauss's law tells us that this expression is equal to the charge enclosed by a constant, that must then mean that this enclosed charge is also zero. Therefore, there's no charge inside a conductor. Now, speaking of conductors, another important thing to notice is that on the surface of a conductor, all the field lines are actually perpendicular to the surface of the conductor. You might be saying, how can this be? Right? It's the same reasoning that the electric field within a conductor is zero, is that if all the charges are on a surface, and if there's an electric field perpendicular or not parallel to the surface, just in a sideways way, for example, not perpendicular to the surface, what's going to happen is that means the charges are going to have to move, but they can't move, otherwise they're not in equilibrium. So to reach an equilibrium state, all electric fields coming from a charged conductor are going to be perpendicular to the field. That's pretty cool, right? And the last important thing about conductors is that if I have a hollow conductor here, so let's say this is a conducting sphere and it's hollow, and I apply an electric field to the object, something extremely interesting happens. And this phenomenon is known as electrical shielding, but essentially what happens is that all the protons are going to be moved to the side here, right? All the charged particles, positively charged, are going to be moved here, while the negative charged particles are going to move opposite in the direction of field lines. And what happens is that because these charges are now distributed along the conductor, the surface of the conductor, there's another electric field inside that goes from the positive to the negative. But since there's an electric field also coming in from the right, what happens is that this is called the superposition of electric fields. These fields actually cancel out. Because if we have, let's say again, using our definition of an electric field, placing a positive charge within the center, it's going to be pushed to the right, it's going to be pushed to the left. We can add up these forces and we'll get a net zero force. Meaning that inside a conductor, a hollow conductor, the electric field is zero. There's no electric field here. Even if there's a field on the outside. And this phenomenon is known as electric shielding. So something important that I actually neglected to mention is that in regards to electric flux, there's another, just because electric flux is zero doesn't automatically mean that the electric field inside is zero. This E that we have in our integral has direction. And what that means is if there's an electric field going inside the surface, that's a negative electric field. But on the other hand, if it's going outside, we take it as a positive. If it's going through the surface from the inside to the outside, that's a positive. If it's going from the outside to the inside, it's a negative. So if I just have a Gaussian surface here, and I have electric field lines passing through it, there's no charge in here. But the electric flux is zero, because the lines are going in and going out. That's why for this example of this conducting spheres, it's not enough to just draw this Gaussian surface and say that, oh, therefore the enclosed charge is zero. We need to clarify that there can't be an electric field in the first place because of what we talked about earlier with the equilibrium. I'm sorry for neglecting to mention that. I hope this isn't too confusing. But moving on. Now, we can also use Gauss's law to prove what the electric field is from certain objects. So let's say, for example, that I have a line, a straight line that goes on for infinity. And it's charged. So how can we talk about the charge of an infinitely long surface? What we can say is that it has a linear charge density, denoted by lambda. And what this means is that, let's say, for example, it has a charge of 3 coulombs for every meter. So if I take out a meter of this infinite line, it'll have a charge of 3 coulombs. Right. So how can we find the electric field of such a surface? What we can do is, if we selectively take a cylinder as our Gaussian surface, and let's say it has a radius of r and a height of h, and this is our infinite line, what we'll note is that, as we talked about earlier, the electric field lines are going to be perpendicular to the line. They're going to be spreading out in every direction. And what's important to note is that at the top, there's no electric field lines going through the top, because, as I said, they're all perpendicular to the line, so it's just going to be outwards like this. So we don't have to care about the top for our area, because there's no electric field lines going through that area in the first place. But essentially, if we set up our integral for finding the electric flux, we'll have E times dA times cosine theta. But in this case, because the field lines are perpendicular to the line, the infinite line of charge, this cosine theta is just going to be 1, because they're perpendicular to the cylinder, the walls of the cylinder. So, and because it's a cylinder and it's a constant distance away from the line, we can actually pull the E out of the integral because it's a constant. So we're then left with the closed integral of dA. And what that just means is E times the total area, the total surface area, of the cylinder, minus the top and bottom. And those of you who know geometry will know that this is equal to E times 2 pi r h. Now Gauss's law tells us that this is equal to the charge enclosed divided by a constant, epsilon naught. So what is the charge enclosed? Well, it's just the charge of the part of the line that's inside our cylinder. So how can we find that? Well, we know that the cylinder has a height of h. And since we know that the linear charge density, we know that it's lambda, we can write that the charge enclosed is lambda times the height. Now take a minute to think about this for a second. Is that linear charge density is going to be charge divided by a length, and we're multiplying by the length of h, so that we're just going to end up with a charge. So if we set this equal to our expression that we derived, e 2 pi rh, we can cancel out the h's, and what we'll get is that the electric field due to an infinite line of charge is going to be the linear charge density divided by 2 pi epsilon naught r. Great. So what's our takeaway from this problem? The takeaway is not just that, due to an infinite line of charge, the electric field is lambda over 2 pi epsilon naught times r. Our takeaway is that given an unfamiliar object with a charge, if we smartly select our Gaussian surface, in this case the cylinder, which with a known surface area, we can avoid taking the integral of some complicated function, and we're able to find the electric field just through basic math. So that's the key takeaway, is selecting your Gaussian fields carefully and specifically. Let's talk about another such shape. Let's say now that instead of an infinite line, I have an infinite plane. And I'm drawing these arrows to show that it goes on for infinity. And it's charged. Specifically, the charge is expressed with something called the volumetric charge density. Denoted by sigma, it's going to be your charge divided by your area. So, sorry, this isn't volumetric charge density, it's surface charge density. But anyway, for an infinite plane, what happens is that we have this surface charge density denoted by sigma. And the way that we're going to solve for our electric field here is if I take a sideways view of our plane, so pretend it's a charge, we make our Gaussian surface another cylinder, except this time we make it perpendicular to the surface. And what we find that is, because these lines are parallel, correct? So what we have here is we have our E electric field times our dA is equal to our charge enclosed. So our charge enclosed is going to be our surface charge density times the area that we're cutting out. Now, if I look at it from the front, it's going to be a circle. So this is going to be, if we have an arbitrary radius r, it's going to be pi r squared, right? That's the area that we're cutting out, divided by epsilon naught. Now, once again, our E here is going to be a constant, and we're taking our dA. is equal to this value. But for our dA, right, if we integrate it, and again, it's our electric field lines are perpendicular to these flat tops. So cosine theta is just going to be 1. We can just say EdA. Now, when we take this integral, if I move over here, we'll get EA is equal to pi r squared divided by epsilon naught. But our A is not just going to be pi r squared, because the electric field is coming from both ends, both caps of the cylinder. And it's going out of both. So what that means is it's actually going to be 2E, E times 2 times pi r squared. Which means if we solve for E, what we're going to get is that E is equal to our charge density divided by 2 epsilon naught. Now, notice that this does not depend on distance away from the plate. So what does that mean? It means that regardless if I place a charge here, or I place a charge all the way out here, the force on that charge is going to be the same. Yes, it seems a little non-intuitive, but that's physics for you. Now, the force on this is going to be the same. The electric field is going to be a constant. Now, this actually takes us to our next example of 2 parallel plates right next to each other. So let's say that one of them has a positive charge and the other one has a negative charge. Now what's going to happen with these 2 plates is that they're both going to extend a field outward. Sorry, the positive is going to extend a field outward in both directions. Right? And the negative plate, negatively charged plate, is going to do a field inward. From both directions. Now you see here that these field lines over here, they're going to crisscross, they're going to meet. And as we said before, the distance from the plate does not matter. This E will always be a constant. So basically, if I put a positively charged particle here, it'll be pushed by the positively charged plate by some amount, and it'll be pulled in by the negatively charged plate by the same amount, as long as they have the same charge density. Which means that the force on that particle is going to be 0, meaning that actually there is no electric field outside of these parallel plates. However, inside the parallel plates, what happens is that the electric field lines are pointing in the exact same direction. Thus, the electric field is going to be doubled. So between 2 parallel plates, the electric field is going to be it's going to be 2 times the E of just one plate. So let's say E naught. Which means that it's just our charge density divided by epsilon naught. And that is the electric field between 2 plates. And the outside, it's always going to be 0. Now let's talk about a couple more things. Right? If we have a spherical conductor, you may have learned in a previous electrostatics class that a spherical electric conductor can be approximated as a point particle at the center of the sphere. Now the question is, why? If I take a Gaussian sphere on the outside of this sphere, so their Gaussian surface, the electric field is going to be pointing outward. correct? On all sides, and our E is a constant. And the field from this conducting sphere is always going to be perpendicular to our Gaussian surface. So cosine theta is just 1. And we're saying this is the charge enclosed divided by epsilon. But what happens is that if we pull out our E and then take our dA, or integrate our dA, we're going to be left with E times the surface area of the sphere, which is just, if you know geometry, it's going to be E times 4 pi r squared. It's going to be equal to Q by E naught. So then if we solve, what we're going to get is Q by 4 pi r squared E naught. And then if you recall, 4 pi E naught is just K, Coulomb's constant. So we get KQ by r squared, which is exactly the same formula for a point particle centered at r. Thus, given a conducting sphere, it has the same electric field as just one point charge with that same charge at the center of that sphere. So what does that mean, right? Now the question becomes, what about an electric field of an insulating sphere, right? So if I have a sphere and it's insulating, meaning that the electrons aren't free to move, or the particles aren't free to move, and let's say the positive charge. Specifically, let's say that it has a volumetric charge density denoted by rho. And what this means is that a charge divided by a volume. Because our volumetric charge density. The question is, what is the electric field? So, there's two cases. One, if we take a Gaussian sphere, like we did for before, there's one where the case is our small r is bigger than our large r, and one where it's smaller than r. So if we take our outside, what happens is that if we take our Gaussian surface, we'll basically get the exact same math that we did for a conducting sphere. Right? We'll get our E, dA. E is going to be constant in this case again. Is equal to our charge enclosed by epsilon naught. Should be an integral. And since it's the exact same equation, same setup, once again we'll get that we can treat it like a point at the center of the inducting sphere. But once we get inside, right? Now there are charges outside of our Gaussian surface. And there are charges inside. And our charge is no longer the total charge inside the Gaussian surface. Now the question is, do these outside charges, the charges that are outside of our Gaussian surface, affect the electric field inside? The answer is no. They do not. Right? And it comes basically, it's something called the shell theorem, meaning that inside a charged shell, a uniformly charged shell, where meaning the inside is hollow, the electric field is zero. Right? And this generally applies to conductors as well, is that inside any conductor, the electric field is zero. And we talked about this before, and we brought out our whole reasoning. So go back if you are unsure why this works. So essentially, we can only think about the charge that's inside our Gaussian surface when we're discussing the electric field. So, once again, our electric field times our dA is going to be constant. So we can pull it out, have our dA. And this time we're going to get E times 4 pi r squared. Correct. And then this is going to be equal to the charge enclosed divided by our epsilon naught. Now the question is, what is the charge enclosed? Well, that's easy. It's going to be our volumetric charge density times the volume, which is 4/3 pi little r cubed. So this is epsilon naught. But then we don't want it in terms of volumetric charge density. We want it in terms of the actual charge that this insulating sphere has. So go back to our formula up here, is that it's a total charge divided by our volume. So our total charge is Q, and our total volume is going to be 4/3 pi big R cubed, where big R is the actual radius of this insulating sphere. So if we substitute that in, 4/3 pi R cubed, what we'll notice is that the 4/3 pi's cancel out. And what we're left with is E times 4 pi R squared is equal to Q R little r cubed over epsilon big R cubed. So we can cancel out the r's, and we're left with E is equal to Q over 4 pi epsilon naught big R cubed times little r. And again, 1 over 4 pi epsilon naught is just k, so it's going to be kq little r over big R cubed. And that's the electric field inside the sphere. So to recap, if our radius of our Gaussian sphere, we're going outside the sphere, right? We can treat it as a point particle. So it's just going to be kq over r squared. But if we're inside the insulating sphere, the electric field is going to be kq r, where r is the distance away from the center, over big R cubed, where big R is the radius of the sphere. And then for a conducting sphere, again, it's going to be kq over r squared. But if we're inside this conducting sphere, as we discussed, the electric field is going to be 0. Please note this key difference. This is for an insulator, meaning where the charge is uniformly distributed along the inside of our insulating sphere. This is for a conductor. And in a conductor, all the charges are concentrated on the outside of the surface, on the outside of the surface, right? Now let's take a look at one more example before we start going into problems, and that is an insulating cylinder. So once again, if we take a Gaussian surface on the outside, it's extremely similar to the line of charge that we did. And basically our math is going to be E dA is going to be our charge enclosed divided by epsilon naught. E is constant, so we can pull it out. Equal dA. And to recap, the reason E is constant is because we're constant distance away from this cylinder. It's equal to Q over epsilon naught. The integral of dA is just A. And I don't know if I was clear about this, but the reason the integral of dA is just A is because we're just saying add up the area of all these little pieces dA. And if we just add up all these little pieces, then we're just going to get A. Specifically where A is the area, the surface area that the electric field line passes through, which means not at the top, but along the sides. So this means that our area is going to be, once again, 2 pi r h. And something I forgot to mention is that the charge for the cylinder, we're assuming that the charges are uniformly distributed, meaning they have a volumetric charge density of Q by volume. Anyway, so E times 2 pi RH is going to be equal to RQ via the epsilon naught. So we can write this as E equal to Q by 2 pi R H epsilon naught. And what we can do is we can also put Q in terms of the volumetric charge density. So Q is equal to rho V over 2 pi RH epsilon naught, where V is going to be pi R squared H, because that's the volume of a cylinder. Yeah, that's not really relevant. But the gist is we create the cylinder outside, and we get this integral, and we get this. It's great. This is for outside of an insulating sphere. Or insulating cylinder, I mean. So actually, what we can do is, I don't know why I crossed it out, but we can actually put this in terms of our linear charge density. So if we do 2 pi RH epsilon naught, the volume of a cylinder is going to be rho pi big R squared, where big R is the radius of the cylinder, H divided by 2 pi RH epsilon naught. So our H's cancel out, our pi's cancel out, and I'll move this up. And what we're left at is E is equal to rho radius of the cylinder squared divided by 2 times how far away we are from the center of the cylinder times epsilon naught. What about for inside an insulating sphere? And again, it has a volumetric charge. This should go on for infinity, by the way. Forgot to mention. But plus. Now we have our inside. So once again, the outside, the charges that are outside, they do not affect the electric field they create. Do not affect the electric field inside the Gaussian surface, and that's because it's an evenly distributed charge, spherically symmetrical. There is no electric field from the outside. The only electric field in our Gaussian surface to care about is the field coming out of our part of our cylinder that's inside our surface. So once again, if we take our integral of EdA, right, and again cosine theta is going to be 1, we'll get E times A so n is equal to our charge enclosed by epsilon naught. So once again, our EA is just going to be E times 4 pi R squared, where R is how far away we are from the center. Our charge enclosed, though, is going to be rho times the volume that we have enclosed. So what's the volume that we have enclosed? It's going to be 4/3. Sorry, it's going to be it's been a long day. Pi R squared H. And sorry, this isn't 4 pi R squared. This is 2 pi R squared H. 2 pi RH is the surface area of our cylinder. Yeah, this pi R squared H divided by epsilon naught. So if we solve, we'll get our pi's cancel out, our 1R cancels out, our H's cancel out, and we're left with rho times R by 2 epsilon naught. So, once again, the key takeaway is not just this formula, but also how we're getting this formula, how we're setting up these Gaussian surfaces. And that's one of the most key important parts of this unit, right? Is setting up our Gaussian surface such that we have an easy way to calculate the electric field. Now, certain tips that I'll give you is that try to set it up so that your electric field is perpendicular to your surface. So in this case, in our cylinder, all the electric field lines were perpendicular, and therefore we didn't have to talk about theta at all, and we didn't have to integrate with cosine theta. It wasn't difficult at all. And select a Gaussian surface so that your E is also constant. Because we're at a certain distance away, we're at equal distance, we could pull our E out of the integral, and we're just left with EA. Simple, right? So to do that, we'd have to do symmetric things, radially symmetric. So I'd recommend a cylinder or a sphere. So to be extremely useful Gaussian surfaces if you're asked to ever find Gaussian surface, or if you're ever trying to find the electric field for something. So before we go to problems, let's just recap what we did because it was a lot. So we started with forces, Coulomb's law. We talked about electric field. Then we talked about electric flux, which is the flow of an electric field through an area. Then we discussed Gauss's law and how it relates an enclosed charge to our electric flux. So just note that, once again, this is electric flux is equal to this is equal to this. Electric flux is equal to our integral is equal to our enclosed charge by epsilon naught. Then we talked about special properties of conductors. And to recap, with conductors, all the charges are going to be on the surface. There's no electric field on the inside of a conductor. And by Gauss's law, there's also no charges in the conductor. All of it is spread out on the surface of the conductor. And there's nothing inside. Then we discussed that for a conductor, the electric fields are always going to be perpendicular to the surface. Then we also talked about that electric field inside a conductor is going to be zero. Inside a hollow conductor is going to be zero. And even if there is an electric field being passed through the conductor, the electric field inside is still going to be zero because the movement of charges will produce an opposing electric field that will cancel out the one applied from the outside. So if you're inside a hollow conductor, you're safe from electric fields. And this is something called a Faraday cage. It uses this principle of electric shielding to protect you from any electric field throughout. Then we started deriving the electric fields of some common objects, like an infinite line of charge, where we use a cylinder as our Gaussian surface, a parallel plate, an infinite plane, where we used another cylinder as our surface. Then we talked about two parallel plates together, and we derived that because of the superposition of fields, the outside would be zero, but the inside would be our surface charge density divided by epsilon naught. Then we talked about an insulating sphere on both on the outside and on the inside. And then we talked about a cylinder, an infinite insulating cylinder with a certain volumetric charge density, both on the inside and the outside. Now we can get into some problems. Now, because of time constraints, we'll only be talking about a few problems, and we'll just be talking about our general approach to these problems rather than directly solving them. The main purpose of today's video was kind of these conceptual issues, because many students face an issue understanding the concept behind Gauss's law, electric flux, Coulomb's law, things like that. And hopefully that all these examples that we derived should be sufficient practice for Gauss's law. With that, let's move on to some problems. In the figure, the four particles form a square of edge length 5 centimeters and charges 10 nanocoulombs, negative 20 nanocoulombs, 20 nanocoulombs, and negative 10 nanocoulombs. What is the net electric field at the center of the square? So this question has to do with the superposition of electric fields. What that means is here, the electric field from Q4, it's a negative. So it's going to be pointing this way with a certain magnitude. Q1 is positive, so we get a vector here with a certain magnitude and direction. Q2, again, will be attracting with a certain magnitude, bigger than the magnitude of Q4, and Q3 will once again repel in the direction. So we have these four vectors, and what we need to do with them is we need to add them up. So because it's a square, what we can realize is if we draw our axes, it's a square, so that means this is a 45-degree angle. This is a 45-degree angle. This is a 45-degree angle, and so on and so forth. So the magnitude of each vector is going to be kq by r squared. This is our formula for an electric field. So r is the distance from the corners to the center of the square, which the mathematically astute among you must realize that it's a root 2 by 2. And if you don't know how we got that, the answer is Pythagorean theorem. So that's our r. And what we're going to do is we simply decompose these vectors into a horizontal and a vertical component. We add them up, and then we should get our answer. Again, due to time constraints, we're not going to be fully solving the problem. Next, an electron is released from rest in a uniform electric field of magnitude 2 times 10 to the 4th newtons per coulomb. Calculate the acceleration of the electron. So an electron has a charge of E, which, if you quickly Google charge of an electron, you'll find that E is equal to 1.6 times 10 to the negative 19th coulombs. So if there's an electric field, what that means is that this is equal to your force divided by your charge, which is the other formula. Therefore, your force on the particle is equal to your Q times E, your charge times your electric field. And then we also know from Newton's second law that the force is equal to ma, which is equal to QE. Thus, A is equal to QE by m, and once you plug in all those values, you should be able to solve for it. Now, this last question is extremely interesting. In figure 23-2, a butterfly net is in a uniform electric field. The rim is like this, and there's a line perpendicular to the field. The net contains no net charge. Find the electric flux through the netting. Immediately, some of you might be busting out your E dot dA. Okay, we need to integrate over the netting. But the netting is an extremely complex shape that is not easily integratable unless you know multivariable calculus, and even then, it's still not easily integratable. So what can we do here? Notice that it specifically mentions that there's no net charge inside the net, meaning that our electric flux is 0. Notice again that there are fields entering the net, and there are fields leaving the net. So if we have our integral of EdA is equal to 0, and we take our Gaussian surface as the net, the surface area of the net, including this rim, what we find is that all the fields, they'll enter through the netting side, right? That's a positive flux, a negative flux. And then after that, the field lines go out of the circular rim. So let's say that this has a certain flux naught, the flux naught, phi naught, and this has a flux phi 2. I guess I should name this phi 1 then. What this means is that the flux entering the net is minus the flux leaving this disk should be 0. Therefore, the two fluxes are actually equal to each other. So all we have to do is find the flux going through the disk in order to find the flux through the netting. And that's simple because it's a circle with a constant E going through it. So it's going to be our area, pi r squared, times the electric field. And cosine theta is going to be 1 because it says that it's perpendicular to the field. Anyways, that's it for today's episode. I hope that you all learned something, and if you have any questions, please make sure to comment below and I'll try to get to it. Okay, until the next video, goodbye.